Hi class, welcome back to another video lecture. Now today we're going to talk about the ideal gas law as well as diffusion. And so today won't be as long, we're just working a little bit more with pressure, temperature, volume relations, and we're going to incorporate the unit mole. And so I've talked about a mole briefly, but I've never really defined it. So that's what I'm going to do right away here. And that is that a mole is just a unit of measurement of an amount of substance. And so this is defined as having 6.022 times 10 to the 23rd particles. And so depending on the application, it's going to be a different type of particle. So for example, when we're talking about gases, I'll tell you that 1 mole is equal to 6.022 times 10 to the 23rd molecules of gas, and so forth. So we'll use mole quite a bit in chemistry. And so if you guys again remember that cutout, Avogadro, this is who came up with it. That's where it came from. So Avogadro's number 6.022 times 10 to the 23rd. And so we're going to talk about how, one moment here. Pressure and volume in gas, they're proportional to the number of moles as well as temperature. And so it's leading to this relationship connecting the 3 parts, pressure, volume, temperature, as well as moles. And this is called the ideal gas law. And so unlike from 5.5, when we had different conditions, this is when the conditions are the same and known. So known and not changing, we'll say. Because remember in 5.5, we're looking at the change from condition to condition. And so this relationship is defined as PV is equal to nRT or PivNert. I don't know. That's just a way that I've used to try to memorize it. But don't worry, I'll give you guys these equations. And so what's new here now is N. So N, that represents the number of moles and so I'll abbreviate mole as MOL. So just like we abbreviate liters as L, moles abbreviation is MOL. And then R, this is called the proportionality constant. Proportionality constant. And so this value will never change whenever you use this equation, unless you are changing pressure from different pressures. And so this is defined because at 1 mole of having 1 mole of gas at 1 atm occupies 22.4 liters at 273 K. So again, these numbers and values come from Avogadro. And so we can solve for R using this equation with those numbers, and we'll figure out what our constant is. And so if we have PV is equal to nRT, solving for R, if P and V are over an imaginary 1, we're moving both N and T to the denominator on the other side, which gives us R is equal to PV over NT. Now we'll substitute in 1 atm times 22.4 liters, all divided by 1 mole times 273 K. This gives us the value of 0.0821. And now the units are messy because it involves all of them, but it is atm times liter over mole times Kelvin. And so this is the proportionality constant when you're working in atm. So if we're working in kPa, this would be 8.314 kPa times liter all over mole times K. But just to keep it simple for today, we will be working in atms. All right. So let's start with a few examples. And so the question here is asking, what is the pressure exerted by 3 moles of gas at a temperature of 300 K in a 4-liter container? So bring back PV is equal to nRT. We are solving for pressure, which means we want to move volume to the denominator on the other side. That means P is equal to nRT over V. Now I'm just going to substitute the values in. So N is our number of moles. So we have 3 moles. R is our gas constant, which is defined as 0.0821 ATM times L over mole times Kelvin, and then temperature of 300 Kelvin. This is all divided by 4, because we're in a 4-liter container, which gives us a value of 18.5 ATM. All right, on to the next problem here. So this one's asking what the volume of a sample of gas is if we have 5 moles and it exerts a pressure of 0.5 ATM at 200 K. So now we are trying to solve for V. So we'll move P into the denominator on the other side. So we have V is equal to nRT over P. Substituting in, N is equal to 5 as we have 5 moles. R is our constant. Then T is 200. This is all divided by 0.500 ATM. This gives us an answer of 164 liters. Any questions so far? Just let me know. I know this isn't live, but just email me or come to my office hours. Hopefully you guys are getting used to the units. I think the hardest thing is making sure you got the units down for each type of variable. And once you get that, I feel like I know I'm starting to move kind of quickly, but the nice thing is you can always stop and pause the video here. All right. Number 3, a sample of gas contained in a cylinder with a volume of 10 liters. At what temperature will 2.5 moles of gas exert 20 ATM of pressure? So starting with PV is equal to nRT. It's asking at what temperature. So we're solving for T this time. That means N and R are going to the denominator on the other side. T is equal to PV over NR. So it is equal to 20 ATM times 10 liters all over 2.50 moles times 0.0821 ATM times liter divided by mole times Kelvin. And so I'm just realizing I haven't showed you guys how the units cross out. I'll show you on this example. And so here, if we are looking for temperature, our units of Kelvin are going to come from here. And so we just have to make sure that we have both on the top and bottom, either of our big fraction or in one of those pieces. So denominator, numerator, that they cancel. And so this ATM will cross out with this one. This mole will cross out with this mole, this liter with this one. And even though K is in the denominator, it's actually in the denominator of a fraction in the denominator. So what ends up happening is if we get rid of everything else, we're just focusing on the units, we'd have 1 over K. Well, there's this thing, when it comes to dividing by fractions, don't cry, flip and multiply. So 1 times k over 1 is equal to k. So that's how you still get units of k. I just want to show you that there. All right. And for our temperature, we get 974 Kelvin. And lastly, let's solve for moles. PV is equal to nRT. Solving for n, or a number of moles, we move RT to the denominator on the other side. N is equal to PV over RT, which is equal to 3 ATM times 5 liters, all over 0.0821 ATM times liters divided by moles times Kelvin at 300 Kelvin. This gives us 0.609 moles. So hopefully you guys are getting used to, getting the hang of using the ideal gas law. Here we're just looking at a specific gas. How does it behave at a certain condition? All right, let's talk about a fusion and impartial pressure first, I guess. So talking about partial pressure, all this is saying is that according to Dalton's law of partial pressures is that if you have a mixture of gases, the sum of all their pressures will equal the total. And so that's just what this formula is showing us there, is that our total pressure is equal to the pressure of gas A plus B plus C to however many gases you have. And so here are some applications of how we would use this concept. And so one thing I want to comment about gas laws is that gases don't really act like this. In an ideal world, yes. And so some of the stuff might seem a little hokey, but this is just what we work with and kind of just what's been defined with a lot of background stipulations. And so let's start with number 1. So the total pressure is going to be the addition of each of the partial pressures. So P total is equal to the pressure from oxygen plus the pressure from nitrogen plus the pressure from ammonia. Sorry. Yes. Or NH3. And so if you total those up, we get 95 kPa. And so here's where it starts to get weird. And so like I said, we're just kind of making assumptions, and this has to do with ratios really for the rest of these problems. And so what number 2 is saying is that we have a mixture of 1 mole of oxygen gas with 2 moles of nitrogen gas. And together they exert a pressure of 150 kPa. So what's the partial pressure of each gas? So we're just going to assume that this is going to be split equally, even though that might not be the case. And so if we have that the total moles is equal to 1 of oxygen, 2 of nitrogen, so 3. We have 3 moles total. We're going to see how much pressure there is per mole. Well, then we'll take 150 divided by 3. That gives us 50 kPa per mole. So for oxygen, the partial pressure that will give, so I'm representing this by capital P for pressure, O2 is the gas. This is going to be equal to just 50 because there's only 1 mole. I'm going to move this over. Oops. Then for nitrogen, now we have 2 moles. So its partial pressure will actually be 100 kPa. Oops. Sorry, didn't leave myself very much room here. All right, number 3. So now 3 gives us percentages to use. So it's as simple as taking the percentage of the total. And so for helium, if we turn 30% into a decimal, 0.300, so don't forget sig figs here. And we're going to multiply that by the total pressure of 150 kPa. That gives us 45.0 kPa. So that's the partial pressure of helium. For argon, they gave us the percent as 70, so 0.700. Multiply that by the total to see its proportion, and this gives us 105 kPa. So really, these problems aren't complicated. It's just keeping all the different ways we can use these properties separate is where things can kind of get tricky. And then lastly, a sample of NH3 is decomposed into its elemental components. If the pressure of N2 equals 40, what's the pressure of H2? So here we're looking at ammonia, and ammonia is made up of nitrogen and helium. So it's saying, now we have to think of the molar ratio of that molecule. So in NH3, you have 1 nitrogen in a ratio of 3 hydrogens. So if 1 nitrogen gives off 40 kPa, then the partial pressure of H2 is going to be 3 times that because of the ratio, which leaves us with 120. All right, and lastly, a fusion. And so we're not going to cover a ton on a fusion. Really, all it is telling us about how quickly that gas is spread out. And so it's defined as molecular mass and density as they decrease and temperature increases, the gases can spread out faster. And so an easy way to think about it is if you hold temperature constant and just compare a light molecule with a heavy molecule, the lighter one is going to be able to move faster. And so an example of a problem that would be asked for pertaining to a fusion would be like this one here, saying that if we have a closed container of chlorine, fluorine, neon, and helium gases, and we open that so they can escape, what's the order of the increasing rate of a fusion? So I'm going to put here high rate of a fusion. That is going to be equal to lower density. And so here, what we'd have to do is we'd have to look up using reference table S. We use that a lot. And these are listed. The densities are listed there. So we're going to look up the densities to try to give us an input or an idea on how quickly these gases will spread out. And so if we do that, we get chlorine has 0.003214 grams per centimeters cubed. Fluorine has 0.001696 grams per centimeters cubed. Neon has 0.0009 grams per centimeters cubed. And helium with 0.000179 grams per centimeters cubed. And so now what's nice about the order that these gases are in is they are in order of decreasing densities. And as density gets lower, a fusion rate gets higher. So because this has the highest density, this is going to have the slowest rate, meaning the one with the smallest density is going to have the fastest diffusion rate. And so the order that we'd want to put it in for increasing would be chlorine, then fluorine, then neon, then helium.